waste time in the video, but my work is above. You should have gone something like this. We converted from moles of BaCl to, or moles of this to moles of product, and you found the limiting is 0.125, so the answer is A. Moving on to gases. So the very first equation you should know is the ideal gas law with this PIV inert, PV equals nRT. R can either be 8.314 or can be 0.0821, depending on what units you have. So if your volume is in liters and your pressure is in ATM, which is I think more often, you'll use 0.0821. You'll use 8.314 if you have like pascals and meters cubed, and you can convert between many of these. So if you don't like using one or the other, you could convert between them. For reference, a meter cubed equals 1,000 liters. So you can use that conversion factor. And for pascals, it's 101.325 pascals per ATM. For the real gas law, we'll get back to it. I want to first talk about kinetic molecular theory. So for kinetic molecular theory, there's 5 points. First is that gases have particles in constant random motion. The particles have negligible volume, and there's negligible IMFs or forces between the particles. Momentum is conserved, it's elastic, and the temperature in Kelvin is proportional to kinetic energy. So there's an equation for that last one, which is the average kinetic energy equals 3/2 RT, where R equals 8.314. Anytime you're using joules, so energy, R is going to be 8.314. Those are in later units. So based off kinetic molecular theory, we can talk about the real gas law. So kinetic molecular theory says that particles have a negligible volume. That's not true. The particles have very small volume. So this, you'll have to understand it conceptually for the AP. You don't have to actually do any calculations with it. But notice how in PIV inert it looks like this with nRT. This V is really the actual volume minus this. So it's really the actual volume is a little bit bigger than this. So it's the actual volume minus this because it considers that the particles have negligible volume. For pressure, there's also a correction factor, and that's because they claim there's negligible IMFs or negligible forces between all the particles. Again, that's not fully true. So the particles have a little bit of forces between each other. So as the particles are moving around in constant motion, they slightly pull each other from these little forces. When they slightly pull each other, they slow each other down. And when they slow each other down, they hit the walls of the container they're in less hard with a slower speed. And so the pressure is lower because they're hitting the walls with less speed and less hard. So the P in PIV inert is really the actual pressure, which is a little bit lower, plus this. So the actual pressure is really a little bit lower than this PV. So that's the real gas law. You may need to understand it conceptually for an MCQ or an FRQ. For Dalton's law of partial pressures, all it means is that if you have numerous gases in the same container, let's say we have a little bit of Ne, we have a little bit of argon. If I have 0.3 ATM of this and 0.2 ATM of this, the container of both of these will be 0.5 ATM. Very simple. All a partial pressure means is the pressure of just that gas. Like if only neon was in the container, it would be 0.3 ATM. So adding those partial pressures gives the total pressure. That's Dalton's law of partial pressures. Now, inert gases are going to appear a lot throughout all of AP chemistry. All inert means is that it doesn't react. So any inert gas is going to more than likely be the noble gas column, which is the last column in your periodic table. It's neon, argon, krypton, all of that entire column. So moving past that, there's one more law that you should know, and it's Graham's law of effusion. All effusion means, I like to think about it like a gas leaving a balloon. So Graham's law of effusion compares the rate at which gases leave balloons. So the law is basically R1 over R2 equals the molar mass of 2 over the molar mass of 1. So notice how if molar mass 2 is very big, that means R1 is going to be very big. So that makes sense. The slower thing is going to move, the bigger and heavier thing is going to move slower. The lighter gas is going to move faster. So a simple MCQ could give you two things and say which one effuses faster. It's just going to be the one with the smaller molar mass. So now let's do a few MCQs to test our understanding. So for this first one, you can pause and read the directions. This is how I set it up. So xe plus f2, we don't know the coefficient of f2, and we don't know the subscript of f. We don't know how many f's there are. We do know there's going to be one xe. And we're told that the xe fully reacts, and f2 starts at 8, and then it ends up at 4.6. That means that xe lost 1.7, and f2 lost 3.4. So notice how f2 lost double of xe. That means that f2 has a coefficient of 2. So I hope that makes sense. Like every time one of these reacts, two of these react. That's why the change in this one is double of this one. So now that we have this coefficient is 2, well, now we just balance. So we have 1xe, and then we have 4f's. That means our answer is going to be xef4, which is conveniently in option C. For this question, I pasted a picture of a manometer. How a manometer works is this is liquid mercury, then you have your gases of interest here, and then because of the pressure of the gas, it'll push the mercury a certain distance, and that gives us the unit millimeters of Hg pushed, and that's a pressure unit. So here we have O2 over water, so we have water and O2. So of course the pressure here is going to be due to O2, but you also have some pressure due to water. As you may know, water has a bit of vapor pressure above it. So this P right here is going to be due to, sorry about that. This P here is going to be due to O2, and also, this is supposed to be O, and also P due to H2O. So our total displacement 161 is going to be equal to 28, which is water, plus O2. So this is a simple calculation. It's an application of Dalton's partial pressures, and we get that C is the answer. For 33, it's asking which is false. You can pause, read the directions. A is true because even though there's different amount of grams, piv nert is based on N as moles. So 0.5 grams of hydrogen is going to be the same amount of moles as 8 grams of oxygen. You can divide by their molar mass. Also remember that these are both diatomic, but they'll give you the same amount of moles, and so they'll have the same volume. So this first one's true. It's asking which is false. Because they have the same amount of moles, that means they have the same number of molecules, so that means B is also true. C, the density of hydrogen is less than oxygen. That's true because they have the same volume as established earlier, and density is grams per volume. And hydrogen has less grams, and they have the same volume. So that means density of hydrogen is less. Average kinetic energy is the same. That's true because the average kinetic energy is 3/2 RT. R is a constant, and they're both at the same temperature. So by process of elimination, it's E, but it's also E because it says the average speed is the same. That's not necessarily true. Even though their average kinetic energy is the same, kinetic energy is 1/2 mv squared. So 1/2 mv squared of one will be equal to 1/2 of mv squared of the other because they have the same kinetic energy. However, one is heavier than the other. So because one m is bigger than the other, that means their v's are also a little bit different. That's why E is false. Moving on to the next question. And the last one for today. Equal masses of 3 different ideal gases X, Y, and Z are mixed in a sealed rigid container. If the total pressure of the gas is 1.0 atm, which of the following statements about the partial pressure of gas X is correct? It is equal to 1/3 atm. Doesn't necessarily have to be true because there's 3 things and they might contribute differently. So this one could contribute 1/2 an atm, this one could contribute 0.01 atm. It's not necessarily equal contributions. It doesn't have to be. It depends on the intermolecular attraction forces between molecules of X, Y, and Z. Definitely not. Has nothing to do with anything. It depends on the relative molecular masses of X, Y, and Z. Come back to that. It depends on the average distance traveled between molecular conditions. We've never talked about that. It can be calculated from the pressure and the volume of the container. Again, no mention of that. So it depends on their molecular masses. And what I mean by that is even though there's equal masses, so each one could have 5 grams, this one could be 5 grams of hydrogen. So 5 grams of hydrogen is going to be like 2.5 moles of hydrogen, while this one could be 5 grams of oxygen, which is obviously way fewer moles, like a fourth of a mole. So it depends on their molecular masses or molar masses. That's what I'd say. So that was it for stoichiometry and gas laws. Let me know if you have any questions. We'll have harder FAQs in a different video. Thank you for watching.